Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Dragos Munteanu, who's visiting from ISI, and he's just finishing up his PhD thesis this spring, I assume? May-ish?
No,
Oh, you're already done?
already
done. Look at that.
Yes.
And he was advised by Daniel Marcoux there at ISI. So here's Dragos.
Thank you. Okay, so I'll be presenting today the work I did for my PhD thesis about exploiting comparable corpora. So the motivation behind my work is the lack of a very useful resource, parallel text in parallel translation. Parallel texts are useful essentially in any cross-lingual NLP field, but they are most particularly important for statistical machine translation, where they provide the training data from which the system learns everything it knows about translation. This chart shows probably a little bit outdated count of the amount of parallel data that are available to the research community. And as it shows, all parallel corpora are between English and another language, a handful of other languages, most of them European. And with a few exceptions, these corpora are relatively small, about 20 million words. And again, most of the data comes from a single domain, translated proceedings of various political bodies, United Nations Parliament, European Parliament, and so on. There are therefore three problems that we are facing. We have too few language pairs, too little data, and too few domains. Now, domain in particular is quite important for statistical machine translation, because such systems are very sensitive to the nature of their training data and will do badly on data that is from another genre. To show you an example, this is a Spanish to English phrase-based MT system that was trained on data on political domain data, and I used it to translate a political document and a sports news document. And as you can see, performance drops by a lot down here. So here you can understand what the document is about. Here there are words it doesn't know. There are strange phrases, pushed traces, shortlisted for membership. So there are all sorts of phenomena that the system doesn't know how to handle because of the training data that it's been trained on. So the solution that I propose to dealing with this shortage of parallel data is to exploit a much richer and more available resource, comparable texts. The comparable texts are not strictly parallel, but related and convey overlapping information. A good example are multilingual news feeds produced by many news agencies and available widely on the web. Right? So if you can think about it, two news articles about the same subject in two different languages are a prototypical example. And these comparable corpora do contain parallel data. So this is the front page of the Agence France Presse website for English and French. And immediately you see they have two articles about the same subject, Sharon's condition. And if you read through the text a little bit, they are talking about the same things. So there is good parallel data to be found. A more detailed analysis of what can be found in comparable corpora reveals three main kinds of parallelism. You may find full parallel documents, which were mostly completely translated from one language into another. And I'll show how to find such document pairs. More often, though, you find documents which share sentences that are parallel to each other, but the presentation is done in a different order in one language and another. there is addition of content in one language or another, and therefore just trying to do something with the full document is harder. What you want to do in this case is to identify only the sentence pairs that are actually parallel to each other and use them for training. And I'll show how that can be done. And finally, the most difficult case is when you don't even have full parallel sentences. All the parallel data that you can find is in sub-sentence fragments, like you see in this example. So there is a piece here, there is another piece here, and I will show a method to identify these pieces and use them also as training data. So essentially, this work, this is the broadest picture, right? You can see it takes a comparable corpus, which consists of two monolingual collections of documents, and out comes parallel data. Now, I do need some bilingual knowledge about the two languages, and I get that in the form of an initial parallel corpus, which I mostly use to train a lexicon. But this setup also allows me to do a very nice evaluation of my results. I use the initial parallel data to train a baseline statistical empty system.
Do they have to be the same domain or different domain?
Can be different domain. And then I go in, extract more data, use everything to train a comparative system. If the second system performs better, the data that I extracted is useful. The experiment that I'll be showing will actually make use of several initial corpora of various sizes, right? I can go from as little as 10,000 words, and that's about 400 parallel sentence pairs. And this simulates the condition of a language pair for which there are few resources available. And the baseline system in this case is going to be weak, but because my lexicon is going to be small, it will be difficult to get good data out of the corpus. At the other extreme, if I train on 100 million words of parallel data, I'm going to have a very strong baseline, which is going to be hard to beat by using automatically extracted additional training data. And I actually also have an experimental condition where I use a regular dictionary, an electronic version of a dictionary. This is, for those who know, it's an LDC collection, Chinese-English dictionary, which is pretty big, actually. It has about 80,000 entries, half of which are one word and half of which are multi-word. But a dictionary is different from a parallel corpus, so it has different properties. It's interesting to see if it can be used. So this is the outline of the talk. I will first give you a general overview of how I go about finding parallel data in a comparable corpus. It will show you how all the pieces come together, and I will also give you an idea of the amount of data that I've been working with and I've been processing. I will then talk a little bit about the lexicons that I use in all the components, and then I'll describe the three main parallel data detection models to find full sentences, full documents, and sub-sentential fragments. And finally, I'll talk about bootstrapping experiments, where essentially if you start with little initial data, you fail to exploit the comparable corpus well enough. You only get a little bit out of it. But then you use that also as more initial data and go in and extract again and again. And it works out very nicely. So I start with two monolingual collections which make up a comparable corpus. The collections I use are the Arabic, English, and there's also a Chinese gigawords, which are available from the LDC. These are pretty big collections, 1.6 million documents here, 600,000 million documents here. And my assumption, Ryan, is that the parallel data that I'm looking for could be anywhere, in any two documents and any two sentences from here. It's true in my experiments I also restrict by, because the articles are news articles with a publication date, I restrict by publication date, but essentially the data could be anywhere. So the first thing I want to do is restrict the search space. And I start doing this by identifying for each Arabic document a subset of maybe 20 English documents that are similar to it. And I do this in a simple manner. I translate every word in the Arabic document using my lexicon. I make a query out of it, I run the query against the collection of English documents, and take the best results, best 20 results. Like I said, in most of my experiments, I don't run over all the documents, but just the ones whose publication date is close to the source. But that's simply a computational issue. So once I do this, and I pair the Arabic document with each of the English ones, I end up with a set of document pairs. And it's about 11 million document pairs. I then, from each document pair, I take all the possible sentence pairs, and I end up considering each one of them. And that's, again, a lot. It's 2.5 billion sentence pairs. So what I do is I run a simple filter to throw out those that are obviously not parallel. Essentially, what I do is I take, I look at all the words in one sentence and check that at least half of them have a translation in the other sentence in the pair. And if that doesn't happen, the sentence gets discarded. And I also do a length check. If the length ratio is greater than 9, again, the sentence pair gets discarded. And so from the 2.5 billion, I end up with 4.5 million sentence pairs that I will actually consider. So now my search space is much smaller. I have a reasonable number of document pairs and sentence pairs that I can start to analyze in more detail. And the first thing I do, I look at each of these sentence pairs and find out which one of them are parallel. And I'll describe in a minute how I do that. I then take a step back and say, well, this gives me 2 million parallel sentence pairs. I then take a step back and say, well, these documents share a lot of parallel sentence pairs. So maybe the documents are fully parallel by themselves. And this kind of analysis gives me 100,000 parallel document pairs. The next step then is to use these sentences which were not judged as parallel and still try to make some use of them. And I will try to find sub-sentence fragments which I can still match and use as training data within these sentences. And I find 500,000 parallel fragment pairs. So essentially, these are the two main steps of the system. One which restricts the search space. It simply tries to identify a promising subset of documents and sentence pairs. And then on this subset, I go in and perform a deeper analysis to find sentences, documents, and fragments. In terms of runtime, this takes a lot of time, about 50 CPU days. And this takes much less time, 6 CPU days. Fortunately, this is highly parallelizable. Essentially, for every Arabic document, I can run it separately from any other Arabic document. So I can parallelize it on many machines. So let me talk a bit about the lexicon. Yes, sorry.
Once you've, obviously taking up all those CPU days makes this difficult, but once you've found that parallel data, do you go back and try and find additional promising documents on the basis of the new information you have acquired? In other words, you restrict the search space by finding promising documents on the basis of a simple lexicon.
You're asking if then I go back and do another restriction of the search space? Only if I do a bootstrapping kind of iteration, but otherwise, no. Essentially, if the initial lexicon is big enough, I get most that I can in the first pass. I don't go back. So the way I compute the lexicons I'm using, I take my initial parallel corpus, word aligned it using Giza++, and then I estimate a lexicon by essentially counting word correspondences in the word aligned corpus. And the simplest way to do this is to just use maximum likelihood, right? These two words, I've seen them together so many times. this English word by itself has been seen so many times, I just normalize and get probabilities. And the problem with that is, as I'll show in a second, word alignment errors produce lexicon errors that sometimes are hurtful. And so I've developed another higher precision method of estimated lexicons using the log likelihood ratio score. So let me go through an example. I have this Romanian word which can be translated as reserved, restricted, or silent. There are a couple of other options as well, so this is not a full table. And in the corpus that I'm working on, this word co-occurs 54 times with this one, 8 times, 9 times with 2 times with the co-occurs, means they have been linked together by the word alignment procedure. There are a couple more, but these are the interesting ones. And so the maximum likelihood probability estimates look like this. And of course, we see that 2 has an unreasonably high probability of being a good translation. And that's exactly the problem of maximum likelihood. And this happens because maximum likelihood doesn't take into account how many times the other word appears by itself, right? And you can see 2 appears 200,000 times, and only 9 of them are connected to my initial Romanian word. So let's see how we can solve this problem by using log likelihood ratio score. Log likelihood ratio scores essentially use all these numbers to compute the score. And what happens is that they give high scores to word pairs which are strongly associated, and low scores to words which are weakly associated. However, association means either that the words occur almost all the time together or almost never together. So it can be a positive association or a negative association. And you can see this here. This is big and this is also big. So a way to distinguish between positively and negatively associated words is to use their joint and to compare their joint probability with the product of their single probabilities. Right? If the joint probability is higher, then they occur together frequently. If not, they don't. And so by this check, we can split down the translations into positively and negatively associated words. And then we can normalize each of them independently and get 2 probability distributions. This one is, let's say, a higher precision lexicon, essentially. I've eliminated spurious translations. This one is some indication of the probability that the is not a translation of my original Romanian word. And I'll come back to that toward the end of the talk, and I'll show you how this is used. But essentially, for now, the important part is that we could clean up the lexicon by eliminating spurious translations and getting somewhat spiker probabilities. So let me go ahead and describe how I find parallel sentences in comparable corpora. See, this is the example that we had in mind. Sentences are mixed up, document contains additional content, and the intuition here is that I cannot rely on context to tell me much about sentence level parallelism. What I want to do is to analyze sentences independently. I just take the 2 sentences and be able to tell whether they're parallel or not. And my approach is to build a classifier able to distinguish between these 2 classes by looking just at the 2 sentences in a pair. And the features for the classifier come from the word alignment between the sentences. I essentially compute a greedy word alignment. I use the lexicon and connect together words which are translated according to the lexicon. And then from the word alignment, I extract a number of features, which tell me how many words, what percentage of words are aligned or not aligned. I look for long strings of interaligned phrases or long phrases that are completely not aligned. I'll use that word fertility, one word connected to many others, and so on. So there are a number of features that I use. And so the sentence pair becomes a vector of features. which I then throw into the classifier and get parallel or non-parallel. The classifier can be trained in a supervised manner by using a known parallel corpus, right? I can take it, shuffle the sentences, and generate positive and negative training instances for the classifier. And likewise, I can measure the performance of the classifier by taking another parallel corpus, mixing it up, and seeing how well the classifier manages to recover the parallel sentences. So I'm going to evaluate my method in an intrinsic manner by measuring the classifier's recall and precision, and in an extrinsic measure by simply applying the classifier on all the sentences in my comparable corpus, the ones that survives that filter which I talked about, which throws out sentences that don't have sufficiently many words translated. I just classify them all, take the ones classified as parallel, put them in the training corpus, see what happens. So let me talk about classifier performance for a second. As I said, all my experiments are replicated with various initial parallel corpora. A smaller initial corpus gives me a smaller and lower coverage lexicon, right? And this effectively has a big impact on the recall. Many of the sentences, although they're parallel, I cannot recognize them because the lexicon is poor. However, the precision results are constantly fairly high, and this is actually more important because we want to get clean data. I also have this experiment where I use the dictionary, and again it has pretty high precision and also fairly good recall because the dictionary is actually pretty big. It's bigger than this corpus. Now, yes?
Do you have any probabilities in your dictionary, or how do you use them?
For this particular task, I don't use the probabilities. The lexicon is used to compute the word alignments. And then from the word alignments, I extract features. So the worse the lexicon, the worse the alignments. And that's how.
For every word in the lexicon, you use all the translations, if any. If
I attempt to use all the translations. Yes. Now, the precision results can actually be improved by essentially using better training data. So in this case, this data came from news domain part of the training data available for Arabic and Chinese English systems. And here I used the political domain data. And although there is a domain problem here, the main effect is that UN data is more literally translated. And training on it teaches the system to be more picky about the quality of the alignments it accepts, essentially. And so
testing both on news.
I'm testing both on news. So the lexicon, the recall is somewhat lower, but the precision is much higher. Now, for the rest of the experiments, I will be using these classifiers, and they will actually give rise to some interesting points. But so the classifier can be made to do a lot better. So okay, let's look at the machine translation experiments. So essentially what happens here, I start with a certain initial parallel corpus, 100,000 words, which, if I train a system on it, gives me this performance. I then train the classifier, run it on the comparable corpus, get an additional 14 million words of parallel data, train a system on these two, and get this performance. And performance improves across the board, and everything's very nice. There are two other interesting points about this slide. One is, for example, the drop in the size of the extracted parallel data that you see here. Right? I start with less initial data, but get more out. And the reason for this is in the classifier precision. Oops, the precision here. Essentially, if you remember at the beginning, I said I run the classifier on those 4.5 million sentences after the filtering. And now once I have those sentences, if the classifier precision is lower, it will classify as parallel more of those sentences. wrongly probably, but it will just get more data out, not necessarily better. And this is the phenomenon that happens here, and you'll see it on the next slide as well. The second interesting point is that, well, for example, this point is almost as high as this point. Here I have 50 million words, here I have 100 million words, and they do just as well. And this is a domain effect. In my initial, so my test data is a news domain. And I tried to use as much news domain data as possible that I had available for the initial corpora. All these are completely news, but here, especially for Arabic English, only maybe 10 million words are news, very little. The rest is political domain data, which doesn't help as much. However, all the data that I extract is also news domain, so it's much closer to the test. And this is why 50 million words give me more than almost as much as 100 million words here. However, this is still a strong result. This is essentially almost the state of the art in Arabic English translation, and it shows that by getting automatically extracted additional data, I can still improve on that as well. So for Chinese English, the improvements are not as spectacular anymore because the Chinese has more news data to begin with. The initial corpora have a lot more news data. And also Chinese is not as sensitive to the difference between political domain and news domain. Not quite as much. We have again this effect of more extracted data versus as we get less initial corpus. And here, for the initial corpus of 100 million words, I failed to get significant improvements. But everywhere else, including the dictionary, my additional extracted data brought improvements. Okay, so I'm going to move on to I'm going to show you some examples, sorry. So these are some example sentences produced by my method. And here's what happens. I have an Arabic sentence. And each sentence, as you've seen, is compared with many other sentences in several other documents. And each of the decision is independent. So the same sentence can be judged parallel with different sentences in different documents. So this one was judged parallel with these three other English sentences. And the bold and italic sentence has been produced by a human. I asked a friend to give me a translation. So as you see, the first automatically matched sentence is a pretty good one. The second is also good, but has some extra material in his capacity as Japan's Prime Minister. And the third one is also has some good stuff, but the meaning of the sentence is actually a little bit different, because here it's talking about provoking strong indignation from China. So this is the kind of range that you expect in automatically extracted parallel data. And these are the probabilities that come out of the classifier, which fairly well do a fairly good job of tracking the actual quality of the parallel data. Here's another example where one sentence is sort of matched to, so this is a sentence about the police investigating an accident, and it's been matched with a sentence about accidents and with a sentence about police investigation. Again, this is a fairly nice example of the kind of difficulty of the problem of automatically finding data in comparable corpora. You have all these sentences talking about all these different things. It's not easy to match them up.
So what do you do here in this case? For the parallel data, you have that Chinese sentence, and then the other two, you combine them as the parallel data corresponding to the sentence?
Right now, what I do is I put it as parallel to each of them separately.
Oh.
And it's not always good, but on the other hand, for example, the word alignment component may be robust enough to only align the good part, and then I learn the right thing out of it.
Is there a cutoff that you use for deciding up to what probability?
In the experiment for the thesis, I just took everything. I also, even the last one. And the improvements are there.
So over everything over what? 0.5? Or?
I'm sorry? Everything over 0.5, yeah. When I did this, for example, our institute participated in the NIST evaluation for MT. And there I put a limit of about 0.7. So I took cleaner data from there.
Yes,
so
when you use this kind of noisy parallel data, do you use any technique that actually evaluate the confidence level before you decide how much you want to use it? That's kind of common thing to do.
It is a good problem. So right now, except for this probability, I have no other good way of estimating the confidence and the value of the data. And I rely a lot on the translation system and the training procedure to filter out the noise and to deal with it. But there is work to be done in this too.
Suppose, just out of curiosity, suppose you remove some of them, like 0.55. The amount of noise that they introduce, did it affect your blue scores in some sense? Do you have a profiling of how much it affected? Or it always increased?
So I haven't measured it carefully, but my feeling is that if I start with a little bit of initial data, like up to 1 million words, even this kind of noise helps. And it gets, as your baseline system is much stronger, quality matters more. So for example, up here, again for our evaluation system, I took a lot more care in cleaning up the data, and we got bigger improvement from that. Here, because I just put in everything, it didn't help as much.
That's the reason why I asked. Because in the last one, for example, it has a small drop in the quality because you used your extracted data. I'm curious, is it because of your cutoff point?
Yes, something like that. So this is a negative example of my method. Basically, it picks up a good translation and a bad translation. This is a completely has nothing to do. And another effect here is that the shorter the sentence, the likelier the system is to make a mistake, because it has fewer links in the alignment, fewer smaller values of the features, and so on.
How does your method pick up the second one?
It's very likely that the close class words were linked. It could be that due to a lexicon error, I don't know, sanctions and mission maybe were linked together, and it created some sort of alignment, and it just said, oh, maybe it's good. But this is also shows you that lexicon is a big part. Okay, so to summarize, in order to classify sentences as parallel or not, all you have to do is compute a word alignment between them, extract a set of features, and put them in a classifier that can give you yes or no answer. Now, an immediate extension of this is detecting parallel documents. Why would we even want to do this? Well, so to be precise, I'm looking for documents which are literal translations of each other and not just similar. And this is an interesting problem in itself. Find parallel documents in independent collections is an as yet unsolved problem. But it also helps to make better use of the comparable corpus, because if you really have confidence that these two documents are fully parallel, you can get better data and more data out of them than just by doing sentences one at a time. The hard part in dealing with this problem is that you need high precision. And you need to avoid false positive. You often will have documents that talk about the same thing, are very similar, but they are not really literal translations of each other. And it's hard to distinguish between these cases. And so what I do is I leverage my parallel sentence classifier and use it to find all the parallel sentences that are shared by two documents, and use these links to effectively make a decision whether the documents are parallel or not. If I have sufficiently many links and they are more or less in the same order, it's likely that the whole document is translated. If I have few links and they are mixed up, probably not. In these particular cases, these two are indeed parallel documents. And here I'm missing the links because I can only look at one-to-one connection, and this is a one-to-many. But still see now if I use this document and run a regular sentence aligner on it, the sentence aligner is able to produce one-to-many connections, and I get all this data for training. Here, these two documents have some piece in common, and the rest is not good. So they are somewhat similar, but not parallel, and I can correctly determine that. So essentially what I do, I take two documents, classify all their sentence pairs, and I decide that the documents are parallel if they have similar lengths. At least 30% of the sentences in each document have a parallel in the other, and most of the links are monotone. At least 90% of the links don't cross each other. I again performed an intrinsic evaluation of this. I asked somebody to annotate a small subset of document pairs and find correspondences in there. And then I ran my method against this gold standard, and I got 90% precision and recall. But again, the interesting evaluation is the extrinsic one. And so here what I do, after I have all my parallel sentences that I discovered and I talked about earlier, I only use them to decide which document pairs are actually parallel. And then I only take those document pairs, run them through a sentence aligner, and use that data as training data. I don't use anything else, any other sentences which I found to be parallel but are in non-parallel documents, essentially. So this is just to test the method. And this graph looks very similar to the one before. The important difference is that the amounts of data here are much smaller. Here I used to have 14 million words. Here I used to have 50 million words. Now I have only 6 and 20, but the same kind of improvement, which says that this data is much cleaner. Identifying full parallel document gives you much higher quality data. And the same goes for Chinese, much smaller values, the same kind of improvements. And I don't have here the graphs. If I put everything together, like I take the documents and then I take sentences from non-parallel documents, I get a little bit extra improvement, but not that much. So to summarize, to find parallel documents, I classify all their sentences, find which are parallel, and check that they share sufficiently many parallel pairs, and they are in the same order. And I can do that for all the documents in my collection. Finally, let's talk about parallel sub-sentence fragments. So this is an example. It's probably too small to be read, I'm sorry, but the point I'm making is that these two sentences have some parts which are parallel, and then some parts which are not translated in the other side. And what I'm trying to do is to extract just the good parts and ignore the rest. And the information that I have available to work with is just the lexicon, which tells me this word here, which I underline, has a translation in the other sentence. And these words also have a translation, and this word also has a translation, and so on. Now, considering this kind of information, the best that I can do, and what I'm attempting to do, is to identify sequences for which most of the words are effectively underlined. Maybe not everything, but most of them are underlined. To identify only those and produce those as my parallel fragment pair. And so I spent a lot of time on this and tried various things that didn't work. And one of what made me eventually enabled me to get an advance is the high quality lexicon that I talked about at the beginning of the talk. Because here, if the lexicon is bad and you have underlined words all over the place, there's just no way you can pick up just the good parts. So having a higher quality lexicon helped in reducing the amount of noise. The second part, which I'll be talking about in a second, the lexicon also gives me a probability of words not being translation of each other. So even though this word, for example, it's a bad example, even though maybe, so essentially I have words which are not translated on the other side, but are similar to something that's on the other side. And it gives me a way of making finer grained decisions. I'll get into this in a second. Essentially, the way I find this particular fragment is to associate to each word a value, which is going to be positive if the word is underlined and negative otherwise. And this is going to give me a sort of a ragged signal, which I then smooth out so that words surrounded by underlined words are pushed up, and underlined words surrounded by non-translated ones are going to be pushed down. So essentially, I start building my word alignment just as before, and to each aligned word, I essentially associate the translation probability of this word pair. And I get here a bunch of positive values. Then for all the other words which are not in the alignment, I associate negative values. Often, it's just going to be -1. But then for those words for which I have this sort of negative association probabilities with something in the other sentence, I keep them closer to 0 so as not to drag everything down too much. And I get this original signal, and I smooth it out by doing essentially an averaging function. Right? Each value, I make the average of the surrounding 5 values, and I get this. And as you see, this one is pushed up by everything around it. This one is pushed down by everything around it, and so on and so forth. And in the end, I pick up the fragment for which the smoothed signal value is positive. Now, unfortunately, this doesn't work perfectly. I also have, for example, here shorter fragments for which the smooth signal value is positive. So I introduced the heuristic of only taking phrases that are longer than 3 words. So, for example, this is just 2 words. I'm not going to pick it up.
When you talk about signal processing, one of the very fundamental things you need to do is that you want to detect outliers.
Outliers.
At one point, screw you up. You don't want to
take it.
screw up all the neighboring ones. Have you tried to think about anything like that?
This is very recent work, so to speak, so I haven't dwelled too much into the signal processing part. So let me show you how this works. Let me show you a few examples of this. So here's how I'll present the example. This is the foreign language sentence and a reference translation. And this is the English language sentence. And I'm applying my methods to them. And what the method will do is keep something and throw out what is not to be kept. So essentially, it will throw out some parts of one or another of these sentences. So in this particular case, what it does is decide that this phrase and this phrase should be kept from the English sentence. And everything should be kept from the foreign language sentence. And in this particular case, it works great because it identifies exactly the extra detail that is in the English but not in the foreign sentence. It picks up the should, for example, and throws it out, which ideally it shouldn't have, but that's a minor issue.
Now, when you add this to the training data, do you add it as an edited sentence pair or a sequence of pairs of fragments?
Essentially, I just, except for this is what the training sees.
Okay, so that's put in as one additional sentence pair.
One additional sentence pair. So here's another example where the 2 sentences are related but not parallel anymore. The list of people who withdrew the money and who withdrew money shortly before. And again, it does kind of the right thing, throws out the part which has no translation. It keeps before. Again, this is the kind of thing you can expect. And so here's a somewhat less successful example. These are 2 sentences that are somewhat similar, talk about TV channels and broadcasting and so on, but they are actually talking about different things. And so what my method does, and you can see this especially on the English side, is to keep 3-word fragments of mostly closed class words. On the end of the, on the, there's a lot of these. These are frequently occurring words. They are all aligned to something. They have all positive values, and you just keep on picking those up. And there is something about the national television channel, but arguably this is not a very useful training sentence pair. And essentially this is right now the biggest problem, the biggest source of error of this approach, the handling of the closed class words, which pop up all over the place and you end up with this kind of short fragments. Anyway, let's see how well this does for machine translation. So the experiment that I ran here, I took all those sentences which I had before classified as parallel or not. I ignored the classification part. I just took those sentences and extracted fragments out of them to see how well the method does. And again, I get improvements, so the data helps empty performance. The improvements are much smaller than for the full sentence or full document that I got. And there is a lot more data which brings smaller improvements, so the noise factor is a problem. But however, something good is there. And the same for Chinese. For Chinese, actually, for this data point where the lexicon is really small, the improvement is no longer statistically significant. In the lexicon computed from such a small amount of data in Chinese is just too noisy. It cannot deal with, my method cannot deal with it. However, if I use the high quality, high precision dictionary, I get large improvements. So dictionary quality is a big factor for this approach. Yes?
Well, in the dictionary case, what is the baseline system built from? Baseline empty system?
Essentially, the dictionary as a parallel corpus, which is not so bad because it has a number of multi-word entries, so it gets something there.
Better than the 10K.
Better than the 10K, but it's much bigger. So it's the amount of data is comparable to this, and it does a little bit worse. So.
I think you said this, but I missed it. This plus fragments is all the fragments that you extracted from everything. This is without, you don't have, there's no sentences in there. You just
I don't use any.
Fragments.
Yes, purely fragments. So the reason why I did this, essentially what you would want to do is try to get whatever sentences you can and then use the fragments on the rest. But for this particular corpora, most of the parallel data is in the sentences. And if I discard that, I have nothing else to pick. And another experiment that is useful that I ran is, well, what happens if the corpus that you're trying to extract from doesn't have parallel sentences? That's where, again, another place where you would expect the fragment methods to be of help. And such a corpus is the BBC corpus from which I showed the original example with the Orange Revolution, and which turns out it doesn't really have too many parallel sentences. So this is on Romanian and English, and I had initial corpora of 1 million and 10 million parallel words, and I got, I don't know, on the order of 10,000 Romanian documents from the BBC and a lot more in English. And I ran my sentence extraction method, and it fails to improve too much over the baseline because there's no data to get. And then I ran the fragment extraction method, again, on everything, not just sentences which were non-parallel, and it helped a lot more. So this method also has value for noisier corpora, where you just don't have the sentences. So a few words about bootstrapping. Like I said, especially when the initial data is small, you fail to exploit the comparable corpus as well as you could, because the lexicon coverage is pretty small. But then you can extract some data and use it to train a new lexicon and go back in. And this is exactly what I've been doing. So for Arabic English, I bootstrap using the 10,000 word initial corpus, the smallest that I have. And so this is the baseline performance using just this data. And I do one round of extraction, and I end up with this performance. Now, again, for a brief explanation, after an extraction, I essentially end up with some parallel documents, sentences, and some fragments. And I added each of them individually and together, and it makes for a complicated graph. Here, I'm just showing the documents. So I'm just using data from parallel document, which is the cleanest. And I add it right to the baseline, and I get it. So this is, you've seen this in the graph before when I was talking about parallel document. So then after I do this, I use the parallel data that I got, train a new lexicon, do another extraction, get again just the documents in this case, and performance shoots up to here. And if I do this again, it goes a little bit higher. And for Chinese, it actually keeps on growing. I only had time for 2 such iterations, but it would be interesting to see when it stops. So again, this is baseline just with 10,000 words. And after each extraction iteration, the score keeps on growing.
And in this bootstrapping experiment, you repeated the entire process, including the identifying pocket?
Everything from scratch, yes. So a few words about the state of the art before and after. So much of the work in exploiting comparable corpora was focused on finding essentially new lexicon entries. Right? You say, well, I don't know how to translate this word, but this word co-occurs very often with these other words which I know how to translate. So if I move them into the foreign language and exploit the idea that words which are translations of each other should have similar contexts, maybe I can find a translation for my unknown word. And there was quite a bit of work on that. And unfortunately, there was somewhat low precision. It's hard to do. And only small amounts of, let's say, new translations could be found. There were also efforts to find full parallel sentences in comparable documents. And the first efforts were let's just try to find the most similar document pairs and assume they are parallel, and run a sentence aligner which maybe allows for more reordering, and just try to do that. And the results are, let's say, noisy parallel. And again, it was a small-scale experiment. And there was also work by Pascal Fung, who did something similar to what I did, but measured sentence similarity, not by classifying, but by doing a sort of a cosine similarity score and putting a threshold, saying whatever about this threshold is good and what's not. And again, this was a small-scale experiment, and the results were evaluated by hand, so it's hard to compare. And then there was the strand system of Philip Resnick and Noah Smith, who went out on the web and tried to find web pages which are parallel to each other, using a combination of URL similarity, HTML structure similarity, and also content similarity. And this was a fairly large-scale effort, very precision-oriented, so the pages are good quality, but relatively little data came out of it. And most importantly, none of these efforts managed to show that the data that they obtain is good for something else, especially machine translation. So none of these efforts managed to show machine translation improvements. So the work that I've done is able to find parallel data at various levels, fragments, sentences, and documents. I've shown that it can scale to fairly large corpora. I've been able to obtain machine translation improvements from the data that I obtain. And I've also shown that this has potential to be useful for both resource-rich and resource-poor languages, especially if the comparable corpus that you have is large enough, and this is just a problem of getting it off the web. Then you can actually get a lot of good quality parallel data. For future work, there is yet a lot to be done to improve these models by incorporating other sources of knowledge, like maybe syntactic structure, maybe differentiating between closed class and open class words. There is a lot more to do to improve the precision and robustness. And I expect that as I try to handle more and more noisy corpora, further challenges will appear. And there are also many other interesting experiments to be done. So, by example, by aligning data, comparable corpora that come from different domains, it's just interesting to see what comes out of there. Maybe some sort of a general language that is common to both domains, and it would be interesting. One can also align across languages by going from English to Arabic and Chinese, and then this would give me some Arabic to Chinese connection. And the approaches that I've taken can also be applied to other NLP problems. The first that comes to mind is paraphrase acquisition. Simply aligning monolingual corpora should yield an interesting result in paraphrase acquisition. And there are also, for example, the classification approach that I have can be applied, I think, to things like textual entailment, where you want to decide if a sentence can be inferred from the one preceding it. And by just finding the right features, you can just look at any two sentences and decide yes or no. Inference can be inferred or not. So I think there is a lot of contribution that this method can bring to other NLP problems. Thank you very much for your attention. Thank you. Questions? Yes.
So I'm curious in the fragment method in particular. So the new data that you get, since it's based on the existing connections in the existing lexicon, so it can add to your empty training corpus either new phrases composed of existing words. So you've never seen the phrase before, but you've seen those words, or you can learn new words. Now, in the case where you're finding new parallel sentences, you're probably picking up new vocabulary as well. But in the case where you're finding fragments, have you looked at whether you're learning any new vocabulary there?
I am learning new vocabulary, but definitely less than with the sentence.
You can learn new vocabularies if it's smooth above zero by something strongly linked on both sides of it, right?
So I didn't look closely enough at this, but I expect that with the fragments, a larger proportion of the gain is due to simply having the right phrases in there somehow. Even though I knew the words before, I maybe hadn't seen them in those particular phrases. For sentences, I'm sure that I learn a lot of new words because I can. It's the method by which I classify sentences is looser. I can have only a few connections, and then I pick up the whole sentence pair.
Philosophically, I mean, this approach is as follows. You assume that you have a whole bunch of data which may not be parallel, and then you do something to create pseudo parallel which has noise there, and then from that you assume that they are clean, and then you do translation.
True.
Would it be better to think about a more integrated approach? You think everything is noisy. You start with the noisy, corresponding, comparable data, and then you start from whatever a blue score you have. From that you drive back to all different stages.
From the blue score, I drive back to
the way that you select data, the way you do translation. It's kind of integrated approach rather than kind of modular approach. Is there any thought on this?
So the fully integrated approach would also take into account the model on which the empty system is based, and that would actually be a big factor. And then drive the search and drive the kind of data that I extract and the confidence that I put upon it. And this is definitely something that should be a more principled approach. But then, true. But then you are somewhat less general in the sense that, well, now I can just take this corpus and just make it available, and it's a new parallel corpus of. Yes, but if it depends a lot on my particular empty system, it's less useful. Yes.
So it seems to me that there's different methods. This is actually very similar to your question. It seems to me that these methods produce data of different quality. And do you think there's a way within an MT system to, in effect, sort of keep these data sources separate? I mean, because I think right now you just simply put them all together, right? And presumably, you might the largest of these data sources might actually be of the poorest quality, and so.
So one simple way to do it is to simply downgrade, right, the training data that comes from such sources by maybe, I don't know, when doing word alignment by lowering the counts, for example, or when learning the phrase table, for example, phrases that come from this data should somehow have lower confidence, should be used only for backup maybe. which this might be already too strong, because as I've shown, having this data, especially if it's from a domain close to the test data, you don't want to downgrade it too much, because it actually brings in good information. But there are ways by which you could acknowledge the fact that this is less confident data and downgrade it a bit. But there's been little work done on that. And
Do you think your classifier is actually yielding accurate predictions of how, the probabilities are things that you can believe in, or do you think?
So I definitely think that as you raise your threshold, the data is cleaner. It's not going to have everything perfect. So even at, 0, 9, I don't think everything is going to be perfect even there. But it does a pretty good job at tracking the quality, I think.
An obvious way of doing moving in the direction you just suggested would be taking the probabilities, raising them to a hyperparameter alpha,
and using those to downgrade.
And weighting the counts that you get according to that, and then tuning that hyperparameter would tell you, basically how much you should downweight things that the model's less confident about.
Assuming that the probabilities are related at all to the.
Well, if I'm making that assumption based on the examples he gave, where the quality of the match did seem to be pretty much monotonic in the probability.
Yeah. There's also the possibility that you might just simply want to have an additional scaling factor depending on the source of the data as well. In other words,
yeah, just divide it into chunks.
Yeah.
But that's also the case. Even in the publicly available parallel corpora that we have, they are not of the same quality, and there's a big issue in figuring out which help and which don't, and how much. And people have been going in an ad hoc manner about this. I did some experiment and I figured out this corpus doesn't help too much, and it's better not to train on it. And this one seems to help. Let's put it in. So. Yeah.
So. At several points in the talk, you mentioned the issue of closed class words and how they, for example, can create these very bizarre sort of fragment matches, and even in the sentence classification, some of the misclassifications were short sentences that were mostly function words. So have you done any work to try and deal with this?
I haven't. So I thought about it. But I haven't done any work on it. Essentially, what I would do is simply identify somehow the closed class words and maybe give them less weight, or maybe not allow them to participate in the alignments on which I make my decisions. So there are a number of ways, but I haven't done any work on that.
Do you use any tools, linguistic tools like a shadow parser or a parse tagger in any of the languages to improve the extraction quality? Or do you think it'll help?
So definitely using a parser should probably help, but I haven't done any work on that. Part of the future work, definitely. Yes.
So I was surprised that when you did this fragment-only approach, that you got any gains at all, because I would have thought that it would just destroy the quality of your target language model. But do you have any
So I don't use that data for language modeling. That's one thing. Another thing is, the system that I used was a phrase-based system, which is more robust than others in dealing with just random sequences of words. If I would have used a more syntactically informed system, fragments might not have helped. And I would anyway need to take care and keep the fragments that I extract aligned with constituent boundaries that are used by the system. So it would be more difficult. So the phrase-based approach was good for that.
And then do you use did you use an SVM or Maxent? What was the
maximum entropy.
So you had to generate negative examples from your data in order to train this classifier. How did you pick the right balance of positive versus negative to generate? Right?
So I did two things there. One is, when generating negative examples, I still picked sentence pairs that had a lot of words in common according to the lexicon. So that would have passed that filter that I mentioned. Because if they don't even have words in common, there's little educational value in having that example. And this already kept the balance close enough. But if the number of negative examples was too big, what I did is for each, let's say, Arabic sentence, I would get one positive and few negative examples. And this way, the factor difference would not be more than 2 or 3. So it was simply throwing out negative examples using these 2 principles, that the negative example should still be somewhat similar, and I should have one for each training for each sentence.
The balance is going to have a huge effect on the prior probability. Right? If you have 3 times as many negative as positive, then your prior is
I think I kept
negative.
it almost to 2. I didn't let it go to 3. It would. And I did experiments where I didn't throw any negative example and it was terrible. So it mattered. Okay, anything else? Thank you for your attention.